Granite is one of the strongest stones on Earth, and it's the darling of today's interior decorator. As a building material, it's timeless, elegant, and resistant to acid rain. Nature's granite factory lies many kilometers beneath the Earth's surface. Boiling molten rock called magma builds up pressure from the intense heat and rises through cracks and crevices in the Earth's crust. As it rises, it slowly cools and solidifies into granite. Most granite is buried under sedimentary rock, which makes up most of the Earth's surface. They start by outlining a section of rock wall up to 30 meters long by 7 meters wide. Then use a gas flame to burn long, narrow channels to free up the sides. Holes are drilled 7 meters deep along the bottom and the back. Explosive cable is then fed into the holes. The explosion detaches the section. They then use a combination of drills, steel pegs, plates and wedges to cut it down until they have a rough block measuring 3 meters long by 1.5 meters wide and deep, the size most granite factories can handle. The blocks may be small, but each one weighs more than 20,000 kilograms. At the factory, the first cut is called slabbing. They use a saw to cut slabs more than 5 centimeters thick. The blade's metal segments contain synthetic diamond particles, which create the friction needed to make the cut. Water keeps the saw from overheating. It's a slow process. The saw cuts less than 2 square meters of granite per hour. They use a gang saw to cut slabs thinner than 5 centimeters. This saw has steel blades, tense enough not to bend under the pressure of cutting, and calibrated to cut as straight as possible. The gang saw cuts at a rate of about 8 square meters per hour. It takes 3 entire days to cut through the rough block. Once a slab is cut, it goes for polishing. This is what will bring out the beauty of the stone. The polishing line has 19 heads, each of which has 6 bricks that polish by abrasion. The polishing line processes about a square meter of granite per minute. For a high gloss finish, a slab goes through all 19 heads. For a semi-gloss finish, it goes through just the first 10 heads. For a rough finish, slabs skip the polishing line altogether and instead go through a process called flaming. With a stream of water to keep the slab from cracking under the heat, a propane flame is passed across the surface. This intense heat makes the quartz inside the granite explode, creating a rough surface. This is often used for non-slip flooring. After the finish, the last step is to cut the slabs to specifications. The interlocked minerals that give the stone its trademark speckles, together with remarkable strength, will always be a byword for style and longevity.
You could say that interlocking concrete pavers came out of the rubble of World War II. In post-war Holland, there weren't enough clay pavers to rebuild city streets, so the Dutch began making concrete pavers. The Germans refined the technology and exported it to North America, where they found a quick road to success. Call it a concrete solution for paving. These pavers are solid, and the interlocking design disperses weight, easing the load on the road. To make these pavers, a conveyor belt delivers concrete sand to a weigh belt that weighs the coarse sand as it falls onto it. The weigh belt carries the sand forward, while another conveyor belt unloads stone chips to be weighed. These chips are no larger than 1/3 of a centimeter. The ratio of sand to stone chips varies, depending on the type of paver being made. The weigh belt transports the stone chips forward, along with the coarse sand. Both are en route to the skip hoist. They spill off the conveyor into the skip hoist, which is essentially a bucket on rails. Cables pull the loaded bucket upwards. It stops about 9 meters up, just above a big concrete mixer. A trapdoor opens and dumps the sand and stone chips into the mixer. 6 giant steel paddles mix and then rotate and mix again, while cement is added automatically through several nozzles on the side of this enormous mixing bowl. Making pavers is a bit like baking cookies. Too much or too little liquid in the batter, and it won't bake properly. Water is added until the consistency is just right. Nozzles also shoot a pigment into the mix to tint it. The mixture looks dry and crumbly, but the recipe gives it just enough moisture to form the concrete. Now a filling wagon spreads the mix over a steel mold containing up to 50 paver-shaped cavities. The mold press head applies 10 tons of vibrating pressure. This pulsating force compacts the mixture into the paver mold and removes any air pockets, which could weaken the pavers. Hydraulic cylinders lift the mold, leaving the pavers on the press board. The press board slides out, and the mold once again gets filled in and makes another 50 paver stones. It only takes about 10 seconds to mold, compact, and release a batch of pavers. The press boards filled with pavers slide into a rack. A hydraulic chain hoist lifts each board into a large holding rack. There, a special moving wagon called a finger wagon picks up all the boards from the rack in just one move. The electrical wagon moves along a rail to a curing kiln, where it's almost 38 degrees Celsius. The pavers actually generate the heat due to a chemical reaction from the combination of cement and water. About 12 hours later, the finger wagon carts the pavers out of the kiln. They're now 70% cured as a result of the chemical process that binds the cement, sand, and gravel, causing the pavers to harden. The rest of the curing will happen over the next 28 days. The pavers are now sturdy enough to handle, so 4 steel arms with rubber pads move in and straighten the stones on the board. These alignment arms are hydraulically driven. They arrange the concrete pavers so they interlock snugly. Now, hydraulic clamp arms lift the pavers off the board and begin to pile them up. They're making a cube of stone. This stacking machine is called a cuber. It packs 9 or 10 layers of pavers on top of one another to make this cube. The cube is actually called a bundle. It will be strapped and shipped out to the job site. These concrete pavers will be on the road soon, in more ways than one.
Many people confuse the terms cement and concrete. Cement is a fine grey powder that's used to make concrete. It's also an ingredient in the mortar laid between bricks and stones. Cement also goes into soil cement for paving roads and lining reservoirs. We take a look at the hard stuff. The action begins at the limestone quarry. The limestone near the surface has a high content of the minerals silica, iron and aluminium oxide. Deeper down, the limestone is more pure, containing less of those minerals and more calcium carbonate. The plant uses both types of rock, altering the proportions to make different types of cement. Workers drill holes in the rock wall in which they plant powerful explosives. For safety, the workers have to position themselves behind the area they're blasting, maintaining a distance of at least 50 meters. After the explosion, loaders move in. They transfer the limestone rocks to 50-ton capacity dumper trucks. The trucks then haul their cargo to the cement plant nearby. At the plant, the trucks dump the rocks into what's called the primary crusher. The primary crusher reduces the large rocks to about the size of tennis balls. There's a constant spray of water to keep the dust from billowing up and settling on the chutes. From the primary crusher, a conveyor transports the rocks to the secondary crusher. It reduces them further to about the size of golf balls. Rock high in calcium carbonate and rock low in calcium carbonate are crushed separately. Now it's time to mix the two. The ratio varies according to the type of cement they're making. This overhead machine called a tripper makes piles of the required proportions. They call this the raw mix. Then a reclaimer loads the raw mix into a grinding machine called a roller mill. Depending on what minerals are already naturally in the crushed rock, the factory adds extra minerals, such as silica and iron. Certain types of cement also require aluminium oxide. The roller mixes and grinds the ingredients uniformly, producing a dry rock powder called the raw meal. Now the powder goes into a preheater. The temperature of the powder is 80 degrees Celsius upon entering. Within 40 seconds, it reaches 800 degrees. This begins the process of bonding the minerals together so that they'll later harden when hydrated with water. The preheater is equipped with what's called a flash calciner. In about 5 seconds, it removes 95% of the carbon dioxide in the powder through a chemical reaction. This isolates the lime, which is the most important element in cement. The powder moves into a rotary kiln, a huge cylindrical furnace, where it moves from top to bottom. The kiln rotates at 2 turns a minute to ensure the material travels through at the right speed. The gas flame reaches a scorching 1700 degrees Celsius. As the powder reaches the 1500 degree mark, it fuses into marble-sized pieces called clinker. As the clinker leaves the kiln, large fans cool it down to 60 degrees Celsius. It's important to cool the clinker quickly in order to have quality cement. From here, the clinker goes into the storage area. The last stage of cement making is called finish grinding. They add some gypsum to the clinker. The precise amount varies with the type of cement they're making. Gypsum delays the cement's setting time so that it can be worked for up to 2 hours before hardening. The cement mills are called ball mills because they contain metal balls, about 150 tons of them in the largest mill. As the mill rotates, the balls crush and grind the clinker and gypsum into a fine powder. So that's cement. Nothing hard about that. Asphalt is a black liquid substance that's a byproduct of processing crude petroleum. It is a key component of waterproofing and insulation materials. It's also used for roofing shingles, but its best known use is for paving roads. Asphalt cement is a byproduct of crude oil, and it's this ingredient that's mixed with crushed rocks and other minerals to make paving asphalt. Production begins at the paving plant's quarry, where some 15 metres below ground, workers driving heavy machinery collect boulders of granite that have been blasted off the rock walls. Trucks transport the rocks to the paving plant, which is right on the quarry site. They dump their cargo into the primary crusher, a machine whose steel jaws crush these big rocks into pieces smaller than 20 centimetres. It takes a huge amount of force to crush solid rock. The flywheels that amplify the motor's energy weigh more than 6 metric tons. The primary crusher empties onto a mobile conveyor belt, which transports the crushed rocks to an outdoor storage area. When it's time to make the asphalt, the rocks travel via a conveyor belt from the storage area to a screening building to be classified by size. There, the rocks tumble downward over a series of inclined screens, whose largest holes are 10 centimetres across. Pieces too large drop through and go to a secondary crusher that reduces the rocks to 10 centimetres or smaller, then sends them to a third or tertiary crusher that further reduces them to 2 centimetres or smaller. Rocks small enough to pass through the screens bypass the secondary crusher and go directly to the tertiary crusher. After this last crushing stage, the largest stones are 2 centimetres in size. Everything smaller than 5 millimetres goes in one pile. That includes stone dust created by the crushing process. Stones 10 to 14 millimetres in size go into another pile. Stones 5 to 10 millimetres into another. Trucks transfer material from each pile to separate compartments called feed bins. Exactly what goes into the paving asphalt depends on what's being paved, but generally these are the 4 ingredients. Sand, stone dust, 5 to 10 millimetre stones, and 10 to 14 millimetre stones. The ingredient proportions vary according to what the paving asphalt will be used for. Stones, along with sand and stone dust as fillers, usually make up about 95% of the mix. The remainder, added later, will be liquid asphalt cement. Each bin releases a specific amount of material onto a conveyor belt running underneath it. The belts lead to a main collecting belt that dumps the combined ingredients onto yet another belt that leads to a dryer. The drying process, which takes about a minute, removes all traces of humidity. This will enable the materials to bond better with the asphalt cement. Screening equipment then re-separates the dried ingredients, making it possible to weigh out precisely the required amount of each one. Everything then goes into a mixer. As this demonstration shows, the mixer blends everything thoroughly. Then it's time to pump in hot asphalt cement. Oil refineries make asphalt cement from what's left over after they've processed crude oil. The paving mix contains about 5% asphalt cement. So, if you want to make yourself a paving asphalt cake, take 1 healthy portion of hot asphalt cement and stir well. The ingredients should bind in around 30 seconds. The mixer empties directly into trucks destined for the paving site. There, a paving machine will spread the hot asphalt on the roadbed. Then a compactor roller will pack it down. After about an hour, the asphalt will have cooled and hardened, and it's then time to hit the road.
Clay pipes are part of a major underground network, one that's dedicated to proper drainage. We flush without thinking, but it may surprise you to learn that clay pipes have been serving us well for thousands of years, ever since the days of ancient Babylonia. These pipes can take a lot of stress. They bear the weight of soil and structures overhead, and they won't corrode. They start with scrap clay from manufacturing, raw clay, and shale. After these materials have been roughly processed, a loader scoops the mix onto a conveyor that takes it to a mill for a finer grinding. At this point, the mix has about 10% natural moisture, but it's not enough for it to stick together. So they add more water as it falls into a mixer. The mixer evenly distributes the water in the mix, then moves it towards an extruder that pushes the clay through a pipe-shaped die. The clay pipe that emerges is 20 centimeters in diameter, the size that typically serves a residential side street. It has a bell-shaped opening. It's the female part of a joint that will fit to the male end of another pipe. A rotating blade trims away the ragged edges. Then, an automated system loads several pipes at a time onto a rack to await the next step. Over on another production line, they're making flue liners for chimneys. Is fairly soft at this point, so lettering wheels easily engrave information, and they can cut it to size using only a thin wire. An upender lift stacks it on a pallet to await further processing. Elsewhere in the plant, a main trunk sewer pipe is born. With a diameter of over 38 centimeters, it's big and needs a substantial trim job to get rid of the rough edges. It weighs well over 300 kilograms, nearly 5 times that of the residential pipe. Once they're fabricated, every clay pipe goes into a big dryer for at least 24 hours. A trip through a kiln will toughen them up even more. They'll spend about 50 hours in here, exposed to very high temperatures. This step is called vitrification. It fuses the mineral particles together. They tap each pipe with a hammer to test if it's solid and perform a thorough visual inspection. Lengths of pipe together, they pour polyester resin into the female joint molds that have been placed in the bell-shaped pipes. The resin hardens, forming an O-ring, and the primer, brushed on earlier, helps the new resin joint adhere to the clay pipe. Next, they make a male joint by pouring resin around its spigot end. This will make for a joint with a tight seal. The joints by pumping water into the pipe. Then they raise it as they place a load on the joint. How much pressure will this joint take without failing? Over a metric ton, which more than meets industry requirements. Now they do another type of test on a basic clay pipe. A hydraulic jack applies pressure on the pipe. The number on the gauge far exceeds the burden of being buried underground. And so these pipes are now ready for civic duty down in the sewers.
Most underground sewer and drainage pipes are made of reinforced dry mix concrete. Reinforced refers to the fact that the concrete has steel bars inside it for added structural strength. Dry mix refers to the type of concrete. You can mould it, then immediately extract it, and it holds its shape. Concrete pipes come in a range of length and diameter, and they have a 100-year lifespan. Dry mix concrete is made of stone, coarse sand, Portland cement, which is a finely ground blend of clay and limestone, water, and a chemical that acts as a water reducer. Trucks unload the sand and stone into outdoor storage bins. The materials automatically drop onto a conveyor belt, which transports them to storage silos above the factory floor. The cement arrives by cement tanker, which blows it into a silo. All the silos feed the mixer. As the ingredients blend, the cement and water combine to form a paste. That coats the sand and stone. The water reducer enables them to use minimal water. The less water, the stronger and more durable the concrete. Meanwhile, workers use a special machine to build what's called the cage, a circular steel frame that will form the pipe's internal structure, its backbone. They insert 2.5-metre-long steel rods in a circular configuration, pushing each rod partway through the machine to the other side. There, an automated spot welder fuses a steel cable to one rod. Then the machine begins turning, winding the cable tightly around the rods. Here, a worker is turning the machine manually, just to show us the process in slow motion. This is what it looks like at normal automated speed. As the rods pass through the machine, the welder fuses the cable to them in one continuous spiral. As the spiral cable reaches the end of the rods, the machine's claws spread outward, forming a wider section on the end. This is called the bell section. Workers position it on the base ring designed to hold the cage in place. Then they close a hinged steel mould over it. Now they're ready to pour the concrete. A forklift transports the mould to a machine called the packer head. They position the mould directly under it. A long drill-like screw descends into the mould. As concrete pours in, the screw turns at high speed, moving up and down. Its blades propel the concrete outward against the mould walls, forming the pipe. This process is called centrifugal projection forming. The process for making large diameter pipes is slightly different. A welder fuses spacers to the cage, both inside and out. These will center the cage inside the mould. Workers position the cage onto a base ring, then lower the outer part of the mould, called the outside form, over it. After securing it to the ring, they lower the unit over the smaller inner part of the mould, called the inside form. An overhead funnel pours concrete into the cavity between the two mould forms. Powerful electrical vibrators shake the mould. This forces the thick concrete downward, filling the cavity. This process is called vibration forming. With either pipe forming technique, the moulded concrete is quite fragile, so the moulds go off to the curing warehouse to harden. There, workers remove them, leaving the pipe standing upright. Steam hoses transform the curing warehouse into a sauna. The temperature rises to 60 degrees Celsius. The relative humidity, 100%. The concrete hardens in about 12 hours. Concrete pipes buried underground have to be able to withstand the weight of the earth above them. So the company subjects sample pipes to extreme pressure to test their maximum resistance. Concrete pipes join together with watertight rubber gaskets. Whether it's a robotic arm carrying out those mundane tasks, a glitzy tattoo to impress your mates, or the modern sanitary pad, now you know how it's made.
Ceramic tiles are a popular choice for flooring, kitchen backsplashes, and bathroom walls. They can withstand humidity and won't absorb liquids or odors. They're also fireproof, fade-resistant, and stain-resistant. And no matter how much you walk on them, ceramic tiles never wear out. This factory specializes in wall tiles. Floor tiles are made using the same process, but a different composition of ingredients. The starting ingredient here is talc, a soft, powdery mineral. They blend it with 4 different powdered chemicals, the names of which are a company secret. The ingredients go into a mixer, where they're hydrated until they're 6% water to 94% powder. The mixer runs for precisely 12 minutes. Any longer would heat the mixture and dry it out. The mixture is now slightly damp and quite lumpy. A conveyor belt transports it to a grinder that mills it to a fine texture. This mixture is now ready to be formed into various models of tiles. The factory uses fully automated machinery to produce its 10.8 centimeter square tiles, a standard wall tile size. A moving tray first deposits a batch of mixture into a mold. The mold's cavity is in the shape of 6 upside-down tiles. A press descends, applying both heat and pressure. This compacts the mixture into the cavity, solidifying the shape. As the press rises, the mold automatically pops out the tiles. They roll off the machine onto a conveyor belt. The belt now flips the tiles right side up without breaking them, which is quite a feat considering that these yet-to-be-baked tiles aren't fully hardened. The equipment is precision adjusted to handle the tiles gently at all production phases. A revolving brush now sweeps the tiles clean. Their surface must be free of dust and other contaminants for paint to adhere properly. The factory uses a water-based paint that's specifically designed for ceramics. It continually circulates in the vat, keeping the color well blended. The painting process resembles an automatic car wash. The tiles travel through 4 spray zones, each of which applies a thin coat of paint. Then they pass under powerful heating elements, which dry the paint in mere seconds. All that's left is to bake the tiles, which we'll see shortly. The factory uses the same ceramic mixture to produce these square border tiles. They look just like the other wall tiles, except that 2 of the sides are rounded. When you install a row of these border tiles above the regular tiles, the rounded edges produce a clean, finished look. While the factory uses the same painting process for border tiles, the molding process, as you just saw, is somewhat different. Rather than being fully automated, it requires some manual labor due to the tile's complex shape. That's why border tiles are often more expensive than regular tiles. When the tiles come out of the dryer, workers stack them on wooden racks. They load the racks onto mobile carts, then roll the carts into a gas-powered oven called a kiln. This factory's kiln is 58 meters in length, longer than an Olympic-sized swimming pool, and large enough to bake some 50,000 wall tiles in one shot. The firing, as it's called, takes 14 hours. Any sudden changes in temperature could produce thermal shock and crack the tiles, so it starts out at 200 degrees Celsius, climbing gradually to a peak of 1075 degrees, then descending slowly back to the starting temperature. After a cooling period that lasts roughly an hour, the tiles come out. They're now fully hardened and ready to have their back to the wall.
This company makes 40 different porcelain items. It all begins with a sketch of the piece, in this case, a teapot. A master mould of the piece is created, a negative made of plaster. Craftsmen use it to make a production mould. Porcelain begins as a powder, a blend of 3 minerals, quartz, kaolin and feldspar. This powder is mixed with water to make a wet paste called slip. The mould is filled with slip. Within 10 minutes or so, the porous plaster absorbs the water, leaving a crust of hardened slip. The rest is poured out. After another 30 minutes, the crust has hardened further and the mould can be peeled away to give the first glimpse of the teapot. Excess crust is removed from a different mould for the spout. It's then left for about 10 minutes until it's hard enough to handle, but still soft enough to sculpt. A utility knife is used to open the end of the spout. The edges are smoothed out using a little water and a sponge, and the rim is curved. Next, the handle is extracted from a third mould. Then 12 holes are pierced in the spout side of the teapot to filter out the tea leaves during pouring. Some slip is brushed on to attach the spout and the handle. This model has a wedge along the collar to help align the handle correctly. Other designs have small notches instead. More slip is brushed on to ensure the parts will bond. And the surrounding surface is sponged to smooth out the drips. The piece dries for 2 more days before the lines along the handle and under the spout are carved away and the rim is sanded down. Some pieces are made using a pressure casting system. The mould is made of resin and tiny polyester beads that create pores which absorb the water in the slip. After a hydraulic press closes the mould, the machine injects slip into the cavity. 12 minutes later, a craftsman uses a suction plate to remove what will become a serving platter. He places the piece on a plaster block. The porous plaster lets the underside dry without leaving marks. The items are fed into a large kiln which heats up gradually, taking 8 hours to reach a searing 1000 degrees Celsius, and takes 12 more hours to cool down. Firing hardens the porcelain and enables it to better absorb a coat of enamel. After brushing off any dust, the craftsman dunks each piece in enamel, a protective coating. The porcelain absorbs it right away, and this glaze turns into a shiny skin once the pieces are fired again. Each piece is handled in a particular way to avoid leaving drip marks. During a second firing, the air in the kiln is carefully controlled to produce a pure white porcelain. Reducing the oxygen level removes any undesirable colours. This time the temperature is even higher, 1400 degrees Celsius. The pieces shrink by around 15%. After a quality check, the company logo is added. The transfer bonds when the plate goes back into the kiln for another 12 hours at 850 degrees Celsius. In the end, the porcelain is translucent enough for light to shine right through. Other pieces offer more illustrated displays for a truly fine dining experience.